Hello everyone. So I will present to you BuildXYZ, which is half a research project and half a serious tool for many use cases. It is about automating dispensing of native dependencies. And very quickly about me, if you need my GitHub account, you can find everything you may care about. I'm an XOS developer for a long time. I've been a release manager. I do a lot of low-level stuff, which is related to the boot chain of your computers, and it requires to be trusted. Therefore, you have some serious constraint on how do you package things, their provenance, etc. I'm also a Fig Store contributor, which is a native Nix Store implementation for people who knows about Nix. It has the duplication in mind, content addressability. It has a nice twist about the hashing function, which is not a Git hash trees, but is using Blake-free to enable novel use cases like verified streaming. So this is a work conducted as a master degree internship in the Technical University of Munich, and it's now a free open source project. So if you care about this, please come see me after this talk. So I think everyone is quite familiar with this, the state of things related to this picture. What I want to take away from this picture is that currently our package managers, our build system, have too many implicit dependencies. By implicit dependencies, what I mean is that if you take a project, like maybe a Python project, a Java project, whatever, you can describe a lot of things in the metadata of the package, but you cannot describe very fine-grained things like, for example, this package requires a very specific GPU architecture. We have CPU architecture, we have GPU architectures, and what I take from that is that the software and the hardware is getting more complicated, and we have much more combinations, and our metadata cannot track this. So what we usually find is that this metadata is tracked as code. So my goal with this talk is, and I want to make you understand how BuildXYZ was built and why. So my first goal is I want to stop reading source code to figure out what I need to install, and also README of any project. I want to go into a project and just throw a single invocation in my terminal, and it should just work. So if we are more serious, what we want is we want to have certain properties about the way we run software. So usually we ship big Docker containers or just LXC container, whatever, that contains everything to replicate an environment. But sometimes we do this even for trivial packages. We also don't want to spend time figuring out, tinkering out how to reproduce the environment. And then we also want to have ways to make things work on x86, on ARX64, on any CPU architecture, if the software itself doesn't depend on the CPU architecture. And finally, we should use all this information to improve our own ecosystem at the meta level. So we have a lot of state-of-the-art tooling that I'm pretty sure we've seen represented in this conference. I do three big differences: language-specific ecosystem, PEEP for Python, NPM for JavaScript, Composer for PHP, and much more. System package level manager, you will have APT for Debian, RPM for Red Hat ecosystems, Pacman for Arch Linux, and then you have meta package managers. And meta package manager are what I would say to be package manager that acts between the both worlds. They bridge between language level specific and system level specific package management. You have Conda, Nix, Pack, and much more. And it's interesting in research, most of the artifact evaluations of the process where you give me your research and I run it on my machine and I say, oh yes, I can reproduce your paper, is done by a virtual machine or containers. So maybe an interesting question is, what does research knows about the prevalence of implicit dependencies? So some people ask this question. You can have some references here. And actually, it's not a very well-known studied question. What is more interesting also is that if you go to any language ecosystem and you ask, do you know about the native dependency you need to have for your package? Usually the answer is they don't have any way to specify it. For example, if you take a Python package, there is no real dependency in the libc that you may use for that Python package. It is changing with PEP 725, which is a new PEP to add native dependencies metadata. But even so, cross-language dependency are usually not handled well. Most of the time, a language ecosystem is good only at describing its own dependencies, not the dependencies of another language ecosystem. And then you have some existing solution that does the motivation we just said. I want to run this thing and I don't want to think about the README or the source code. They're very old, and I would say they had this very research goal where you pack your research, have a big binary, and when you run it, it's doing system call tracing to reproduce the environment and faking paths and all on. So my conclusion at the time of saying that, I think, is there is no general solution to figure out build time dependencies in an automatic way or semi-automatic way. So we have a problem statement drawing here. We want to write a tool that wraps existing programs, finds all dependencies it's asking for as it is running. More formally, we want to have a tool that dispenses automatically the required build dependencies to running program. It can run on mainstream operating system. We don't want to be constrained by system call tracing. We don't want to run only on Linux. Nowadays, everyone is kind of having like multiple operating system, macOS, Windows, BSD, and Linux. So we should not constrain ourselves needlessly. It should not have visible effects on the runtime environment. Some research will maybe involve virtualization or performance-sensitive workloads. If you throw at it any random solution, maybe containers, it can create arbitrary limitations. And then you don't want to specify for every build environment what do you need to do to get the dependency. You don't want to hard code everything. And finally, all of this should contribute to that goal of improving the observability of our ecosystems. So an idea may be to say, OK, what is a build system? What is it doing? So on the right, here's a screenshot of the Geeksman page that explains what is a search path. And search paths are usually this piece of information that you can inject into any build system or package management to control its behavior at runtime as to where to look for dependencies. And then when you look for a dependency, what happens under the hood? You're going to be doing a file system call. A system call that does a file system access. And if you collect all the file system traces, maybe you can provide for dependency at runtime. So the idea is we have a Fuse file system. So Fuse, by the way, is a way to build file system in user space. It is very easy to hack on, and is supported by almost every operating system, including BSD. So if you have a file system in user space that you control, that can look and provide for missing dependency, you only have to solve two remaining questions. You need a database to query for the missing dependencies, and you need a list of known search paths that you can interact with. So that's the system that we propose. We have a Fuse file system that is acting as a proxy to the database of packages. Could be APT, could be RPM, could be your own database. It could be Nix packages if you're using Nix. You plug your own database. What is important is we want to have portability, completeness, and minimal performance overhead, which were the goal that we fixed ourselves at the start. So very quickly, I mean, everyone has been seeing build system for all the day and the previous days. So build system automate how to build software, and they handle for you the dependencies, right? You have system and application dependencies. The problem, if you rely only on file system traces, is that actually for the last 20 years, we have been using a nice hack, or maybe not a hack, to detect if you have a certain capability on your system. So you will see it in autoconf-based build system. In order to find out if you support something, you will compile a small piece of code, and you will say, if the compilation succeeds and I can run the program just fine, it means I have this capability. If it fails at any time of the process, it means I don't. So we cannot be blind about providing too many dependencies. It's interesting because it's the opposite problem of the usual problem. Imagine we know about all the dependency, we have to be careful about not giving too many dependencies. Because the worst case is that we're on a Linux system and we give the BSD dependencies, and we make the build system think we are on Linux and BSD at the same time. So not a good thing to do. So the solution we propose is to have policies. Most of the time, you can figure out all the dependencies, and you want to let the user choose, maybe make this a recorded choice, maybe make this a smart heuristic based on the language ecosystem you're working in, or maybe based on the information you can grasp from the ambient system. But make this configurable by the user so that you can like have, you can like ensure correctness. It's important, for example, if you build a program with C, you may want to use the glibc, or you might want to use Muzzle, but there are also other libc out there. Maybe you want to use the Android libc, or maybe the Cosmopolitan libc. So making those configurable or policies is very important to also enable users to just compile things the way they want. So design-wise, the database is called Nix Packages, but it can be any database. You have a user that is running a build system. The build system is building, and sometimes the build system will say, oh, I will look in my search path for some dependency. We'll go through any search path, and if it doesn't find it, the last location should be the fuse file system that we control. And so we will catch the read system call for that dependency that is missing. And then, so you can imagine that the user space on the left, when we do the read system call, is paused. So the word is stopped, and in the fuse file system, we can do whatever we want. So we can take the time for querying a database, we can take the time for downloading the package, we can take the time for whatever we want. And the interesting thing is that if we do all of that, and we answer to the build system, oh, you ask for this, here you go, then what we're doing is we're doing incremental resolution of missing dependencies as we're running the program. So here are the technical details. There are two interesting components. You need the fuse file system. It's only responsible for negative lookups. Once you find a dependency, you don't use it again because it would be a waste of performance. Doing fuse system calls is very slow. You have to do a round trip between the kernel and the user space multiple times. But here, the nice thing is you only have to pay the cost once. If you find about you need a libc include file, you can notice that most likely you're going to access another include file from the same libc package. So whenever you encounter a first missing package, you're not only returning the file, you ensure that the whole package as itself is made available in the second component, which is the fast working tree, which is just a random classical kernel file system tempfs that contains extensions as you go of your environment as you're discovering it. So this way, you maintain low performance overhead for any successive lookup, including lookup of the same package. So it's very important to notice that fuse is really the last resort here. So an overview by example to see what abstract thing I've been talking about for the last minutes. So you may set up your path like this, your search path environment variables. You can see that the last paths are BuildXYZ controlled, and you may get result like this. So the first invocation, you can replace just this by that. Just wrap your invocation by BuildXYZ, and it will set up exactly this behind the hood for you, plus some nice interaction that you can see here. So it will show you debug log. And so on the left, you can see that it's already asking for, I don't have pip in my environment. Do you want to install pip? So at the end, it will say, do you want to install, which version of pip do you want to install? There is some nice heuristic here that we're doing, that we're looking at the popularity graph of packages, and we're sorting the result by that, so that you will always have, usually the first result should be a reasonable result. And that is the case, pip for Python 3.10. And then you can inject this dependency and go on. On the right, you have another example with libffi, which is needed to install this FFI package. The no binary is just here to say to pip that I don't want any wheels, which would defeat the purpose of rebuilding the software. So implementation-wise, so I built this with Fuse and Nix Packages. Fuse is a critical component, but could still be replaced with something else. Nix Packages is not a critical component. The only reason we use it is because it has a lot of packages. And it creates a problem on performance side, because then like if you have 90K of packages, you need to index all the paths of 90K of packages. You find yourself with 20 millions of paths. And like asking, do you have include /xlib.h? can be slow if you don't do it the right way. And then portability-wise, macOS has few support, so it just works, and we don't have to deal with any system call tracing. Bonus, you can use strace with BuildXYZ, which is not possible if BuildXYZ was using itself system call tracing, because you cannot ptrace twice something, which was very useful for debugging. So implementation-wise, for the build system is doing just open system call, right? And the operating system says, OK, I have this file, etc. And then if I don't have it, I will return NOENT, which is no such file or directory in no parlance. And then I will switch to the next search path. So when you do open, in Fuse parlance, what is it? It is translated into a lookup. So you don't know about actually the exact path. You know only about fragment of path. So you have to rebuild the path yourself. And then something happens on the file system side, which I will show you later. But at the end, what counts is that the file system says, oh, but actually this is a symlink to a place I know. And I downloaded this file between this exchange secretly without you knowing. Then you read the link and you're done. On the right, so on the file system side, file system word, while the user space is paused, I search for the path, I find the path, I may be asking the user for, do you want to use this path or not? And then I use whatever the policy return. So we have evaluation. So the evaluation is focused around multiple questions. We run BuildXYZ in fully automated mode. That means we just say BuildXYZ answer yes to any question you think you should answer yes. Of course, we seed it with some policies because, for example, for Python, you have to teach it about the Python packages, like the initial Python packages that everyone is using. And then same thing for like commonly used build systems. And then it can go and package things on its own. It's interesting to see that on Pipey, it's not super good. There are complicated reasons for that. For example, some Python package uses a Rest compiler, and the Rest compiler may require unstable fixtures. And if you provide an old Rest compiler that doesn't have those unstable fixtures, just everything explodes. So it cannot catch for everything. For Ruby games, I think it has a performance of 98%, so it just works, which is quite crazy and super cool. And then there are people who want to use BuildXYZ for other use cases, like they just want to use it for lazy package management. So in Nix, there is this thing called comma, where you just run software without installing it. You just do comma something, and it will download the software for you if you don't have it in your shell. So this is the same idea. You can just use BuildXYZ to run any software you don't have on your system without installing it yourself. The biggest difference with something like comma, which is much simpler, is that it's continuous or recursive. If the software you're installing is asking for another software, then BuildXYZ will install the new software that is being asked for. So it's somehow recursive, big quote, or continuous. It will resolve dependency until satisfied. Also, an interesting use case is automatic packaging. So you have like some repo. We said at the start we don't want to read the README or the source code. So maybe we can use this to automatically not read the source code or the README and to send packages to Debian or Nix packages or whatever. And actually, it kind of already exists. So Nix init is something in Nix packages ecosystem that you can point at a repo, and we'll try to figure out the nice expression based on some heuristics. And it doesn't exist yet, but there is some collaboration going on with me and the author, where we want to plug in BuildXYZ as the last resort layer for finding out about all the native dependencies you cannot find out just by reading metadata, because the metadata doesn't exist. And then you can do final human manual fix-ups with whatever. So to summarize this, in my perspective, providing a native dependency for packages is unsolved. We still are reinventing solutions. We're still trying to find out about standards. We have PEP 725 for Python, which is exciting. I have some reservation about the usage of package URLs. Namespacing and etc. But I think it's definitely a step in the right direction. It's still a very messy experience for a lot of people in research. In research, when you ask about reproducing papers, it's still very hard to do so. We see a lot of wall machine behavior being shipped to something. It is wasteful. We can probably find solution to mitigate the wastefulness, but it's not as perfect as trying to address the whole problem. And so BuildXYZ is just a small contribution. It's portable via Fuse approach. It has high coverage, and it can re-renders implicit dependencies. So maybe you can start this. You can use this to build a data set of all the implicit dependencies of all packages in a package registry. I've been trying that, and it has some improvements to do to get there. But this is pretty much it.
Thank you, Ryan. Are there any more questions for Ryan? Yep, we have one here.
Yeah, that was a really cool presentation.
Thank you.
I'm interested to know about how you handle, so will it only be one distribution that you could like cache against and use as the database at a time? Like, how have you thought about, for example, how do you know where your package is coming from? Will it be in like Nix, or will it be in PyPI? People would need to like know this up front. So how do you handle that, and how do you handle conflicts, for example, in different files?
So I think the answer to that question is, I mean, it is a very policy discussion question. This is a tool that you can take and decide to adopt or not. The nice thing about using Nix is that you don't have to worry about conflicts. As long as you have Nix, you will, even if you're running Debian, you don't have conflict except for GPU drivers and stuff that has to exist globally. So it short-circuits the whole question about conflicts and organization and coordination. Of course, it doesn't solve everything. I don't think, my opinion is that it should not be used seriously. It should be used mostly as a research tool or as a diagnosis tool to improve how we understand implicit dependencies, and we should rather base any serious tool based on the correct metadata. But if you are in a situation and you need a quick tool, that might be this tool that you can use for a quick and dirty packaging experience. That's pretty much my opinion.
Thank you, Ryan. I think we can continue to the next person to stay a little bit on time. If you have more questions, please do it in the Discord and discuss further there. Thank you, Ryan. Big applause, please.